Good afternoon, or good morning, I should say. My name is Bob Kurland, and I'm going to talk today about quantum mysteries and how they might be explained by Aristotelian Thomistic metaphysics. Our first goal will be to discuss these mysteries, and we'll do it in a very elementary way. I hope it will not be too simple for any of you, and I hope it will not be too complicated for any of you. I was told when I began teaching, that you teach to the bottom, and then those who know what you're doing will be grateful or think themselves superior and be grateful that way, and those who have a hard time will be grateful that you're taking time. We'll talk about three types of mysteries: how particles behave as waves and vice versa, the principle of superposition, that is, it's illustrated by the Schrodinger cat thought experiment that I'm sure most of you know about, and then the notion of entanglement. At the left corner, you'll see a cover of an ebook in which I've written about these, and at the right lower corner, you'll see a picture of entanglement. This is a picture taken by pairs of photons. One of the pairs actually takes the picture. That's what you see in the orange image. And the other pair reproduces that, even though it has not taken the image. And you can identify regions on the image and they'll show the same fluctuations, so the images are in fact the same. Well, let's talk a little bit about wave motion, because that's the basis of quantum mechanics. In fact, quantum mechanics was early on called wave mechanics. Here's a picture of a wave. It's a sinusoid, and it moves with a velocity c. This is a traveling wave, and the distance between corresponding displacements is the wavelength, ordinarily denoted as lambda. Here's a real picture of a wave caused by a bee fluttering its wings in water, and you see differences in light intensity corresponding to height and load of the water in the wave. Now, electromagnetic radiation shows wave-like behavior. This was discovered or predicted by Maxwell early in the late 19th century. And what we see here are the red vectors represent the electric field of the wave, and at right angles to that, the blue vectors, which represent the magnetic field, and it travels forward with a speed c, which is the speed of light. And the wavelength, of course, is the distance between corresponding points. Well, let's say a few words about radiation also, because that's, again, fundamental to our ideas. Depending on the wavelength, you have different kinds of radiation. For very long wavelengths, radio waves, they'll have wavelengths of the order of the heights of buildings or humans. Microwaves have wavelengths of the order of animals, humans, butterflies. Then you get down lower and you get infrared, and there the waves become much smaller, the size of the needle point. And still further, you get lower and smaller in wavelength, you get the visible radiation, light and ultraviolet light, and going even shorter, X-rays. And as you see, the scale corresponds to different objects, and it's the objects at that wavelength that the radiation interacts with. Now, there's one other thing to note, is that objects at certain temperatures will emit radiation, and the maximum wavelength of the radiation corresponds to the temperature. And as you go from very high temperature to very low temperature, the wavelength will increase. It goes just the other way around. So that when you have microwave radiation, it's a temperature really pretty low. It's down to almost absolute zero. And the sun's radiation, visible light, corresponds to a temperature of about 10,000 Kelvin, or somewhat lower in centigrade. Well, what does this all have to do with quantum mechanics? Well, it has to do with the way quantum mechanics originated at the end of the 19th century. Classical mechanics, classical physics had done great things, and people thought, well, there wasn't much left to do but find out what the next decimal point was. But there were some unknown things. One of these was the so-called ultraviolet catastrophe, in which that temperature behavior that I mentioned didn't occur. What happened, according to Maxwell's equations and the thermodynamics that could be applied, is that as the wavelength got shorter and shorter, more and more energy got radiated at an equilibrium temperature until finally it went to infinity as you got close to infinity as you got to the ultraviolet. Well, how did Planck in 1900, at the end of the 19th century, beginning of the 20th, solve this problem? He said that the energy, radiation energy, could only be transferred in what he called quanta, discrete packets of energy. And the energy of such a quantum of energy, a packet, was proportional to the frequency of the radiation, so that as the frequency of the radiation increased, the energy in the quantum packet would increase also. And as you see in the formulas here, here's a sort of illustration of how this behaves in real life. We have fireplace embers, a temperature of about 800 degrees Kelvin, and you see they're orange. And then you increase the temperature by about a factor of 2 to 1600 Kelvin, molten steel, and it's white. And the white is really a mixture of blue and red. The blue is starting to really get more intense there. So that as the temperature increases, the wavelength gets shorter, the maximum at which the maximum energy occurs. All right, so what's the next step in this? And I'm using a historical context to show what it's about, because that really explains it best. And my wife, who was a historian, said, you want to know what something is about, you want to see what its history was. In Einstein's great year, 1905, in which he formulated the theory of special relativity and explained Brownian motion, he explained the photoelectric effect. And this was an effect that no matter how intense the radiation that you hit a piece of metal with, if the wavelength was too long, if the frequency was not great enough, it would not eject an electron. However, at a certain critical value, electrons would be ejected. And his suggestion was that light acts like particles, that is, photons. A particle of radiation is a photon, and the energy of the photon is the same as the Planck quantum energy, h times the frequency. So if a photon hits metal, and if its energy is sufficient, if it equals the binding energy of the electron in the metal, it'll eject it. If it has a shorter wavelength, more energy, it'll give the electron some kinetic energy, and you can calculate what that would be. And lo and behold, it turned out to fit experiments. Well, we've seen that the waves can act like particles. What about the converse? Should that hold? De Broglie, the French Count de Broglie, he was actually, in 1924, proceeding from a relativistic background, proposed that particles can act like waves. And he proposed that they would have a wavelength that was equal to Planck's constant over P, the momentum. Now, any proposition in science needs empirical confirmation, and this was confirmed a few years later by the Davison and Germer experiment, in which electrons were shot at a crystal and they showed a diffraction pattern. That is, they behaved as waves, they interfered. And we'll see more about this diffraction a little bit later. But they received the Nobel Prize for this. All right, let's change tacks a little bit. We're still doing history. And what I want to do is to explain or to sort of put into context a theoretical formulation of quantum mechanics that was given by Dirac in the early 1930s. And he introduced what is called the WCAT vector state, so that a quantum state is represented as a combination of independent states. And what you do is you write a vertical line and then a sort of arrow, and inside that enclosure you put some notation indicating what parameters describe the state. And you have the converse, or the conjugate, I should say, of the ket, the bra, which is why it's called bra-ket bracket. So you then say, and this is goes back to some mathematical formulations, that you can write any quantum state as a linear combination of particular basis states. Now that's a little bit simplified, but I'm not going to go into what the non-applications are. So that, for example, if you had two basis states, you could write it as two constant times one bracket basis state plus another constant times the second basis state. And these constants, there can be positive, negative, or complex numbers, and the squares of their absolute values give the probability that you would get either state on a measurement. Now, when you use physics to illustrate this, it doesn't have much intuitive impact. So what I would like to do would be to give you a very unreal and artificial example of the formalism. And let's think about a husband and wife voting. That's very topical right now. The wife could vote Republican, red hat, and the husband could vote Democrat, blue hat, or various combinations. So, for example, if any particular combination was equally likely, wife and husband both Democrat, wife and husband both Republican, wife Democratic, husband, you'd see it like here. And the constant in front would be 1/2, so there would be a probability of 1/4 for any particular value on election. The act of measurement would be the act of voting. So what is, now we'll go back to this entanglement a little bit later. One thing I want to mention here, and this is, I want to interject, this is a quote from Richard Feynman, who won the Nobel Prize for his work in quantum electrodynamics. And he was the first to admit that there are intuitive mysteries. I'll read the quote. What I'm going to tell you about quantum electrodynamics is what we teach our physics students in the 3rd or 4th year of graduate school. It is my task to convince you not to turn away because you don't understand it. You see, my physics students don't understand it. That is because I don't understand it. Nobody does. And there's another famous quote, which is, may or may not be actually attributed to him. If somebody tells you that they understand quantum mechanics, they're either a liar or a fool. So take that for what it's worth. Well, let's go back to this notion of diffraction, the wave, and see how this tells us our quantum mechanical situation. One of the early 17th century, 18th century experiments that confirmed the notion of light as waves is that it showed this diffraction. And what happens if you go to a wave symbolized here on the left with maxima green, minima black, and you let it go through a small hole, it will bend around the corners and become sphere-like, and as shown here. Now, if you have two holes, then what is a maxima in one hole might encounter a dark thing in another hole, and you would get zero. And that's shown in this representation. The blue is zero, yellow is a minima, and blue is a maxima, or the other way around, I'm not sure which. So you see they're interfering. Plus adding to minus gives zero. Now, what we see, in fact, is that particles going through holes or through slits give a diffraction pattern. That's the image I showed you earlier of the crystals and electrons hitting the crystals. In classical physics, you'd have what would be on the left here in this image. You'd shoot the particles through, say, with a rifle or whatever, and they line up in sort of two columns. This is what you'd see on the screen, the pattern, two bands. But if you do this quantum mechanically, you won't see that. You'll see the diffraction pattern. Okay, so that the particles are behaving like waves. All right, well, what does that tell us? Can we observe which slit a particle goes through as it is doing this? No, because if you try to observe which slit a particle goes through, you remove the wave-like behavior. For example, if you either close one slit or if you put a little device to measure before the measuring screen what the particles were coming through, they would behave as if they were particles. You wouldn't see any diffraction. Well, the great American physicist Wheeler put the following thought experiment. Let's think of an experiment in which we don't use slits. We'll have what is called a converging lens, which will separate the impinging light from a laser into two separate beams. And if the beams are close together, they'll show diffraction. If they're far apart, they won't interfere. So what we'll do is to put the screen up and then we'll remove it. And we'll remove it after the light or the particles have gone through the screen. Now, here's the strange part. You remove it after the particles have gone through the screen, but they know that you've removed it, and their behavior changes so that they become like particles. Whoa, did they know that you removed the screen? What happened here? His original experiment was to use a galaxy, a gravitational lens, and then to essentially remove the screen by a basis of beam splitting and reflection. We'll see a little bit how this is achieved in practice. So that this would happen no matter if the emitting particles were millions of light years away. And that's very strange. How could that happen? That would mean that you've gone back in time and changed their behavior. Really weird. So now we'll change tack and talk about entanglement, the other mystery. A pair of particles are produced with linked properties, and the properties are linked even after the particles are separated by a long distance. And these properties are spin, polarization. Those aren't intuitive to many of you. So again, we'll use this voting example. And let's take an example in which the state before voting consist either of the husband and wife both Republican or the husband and wife both Democratic. I'm assuming for the state, to have domestic accord that they'll have the same politics. All right, so after voting, the measurement will be, again, both husband and wife, either one or the other of the two of the pair. Now, this will happen even if the husband and wife are separated. If they were separated, if one was on Earth and the other was on a spaceship going 2 million miles away without any communication between them. And this is what Einstein called spooky action at a distance. Now, does this really happen? Is this entanglement true? Einstein and Podolsky said that their quantum mechanics isn't complete. There has to be maybe some underlying hidden variables that explain how things are going. So the Irish physicist Bell, and this is a great quote, "I am a quantum engineer, but on Sundays I have principles," produced a relatively simple theorem. You can see explanations of that. I've given some in my book that are relatively straightforward. And they predict that if you have separated particles of an entangled pair, the measurements are going to be correlated in a particular way, even when particles are separated. If there are hidden variables interacting locally or by forces transmitted at light speed. Now, experiments were run in which this experiment was carried out. And there's a diagram here sort of indicating the basics of the experiment. And I don't know why physicists usually call separated pairs of this, but they name them Bob and Alice, I guess, after that television show. I'm not sure why, but anyhow. And it turned out that Bell's theorem was violated. So, what can we conclude? There are several conclusions that will explain this. First, that reality is in fact non-local, that spooky action at a distance occurs. Second, that some other kind of reality occurs. What the French physicist who participated in these experiments, who's also a philosopher Despinet, called veiled reality. Or a third conclusion, the experimenter doesn't have free will to choose the measurements settings, superdeterminism. And as I said, the Nobel Prize was awarded to Aspect, Clauser, and Zeilinger, who first did these experiments. Well, let's now turn to theology in quantum mechanics and see if there's any intersection here. Now, there are different ways of looking at these. I'm not going to judge which is correct here. I'm just going to try and sort of give you summaries of what people are saying. The first is that there's no intersection. They're entirely distinct. And you can think about some of the theological positions, but they're really sort of fuzzy, and quantum mechanics is too crazy to really be helpful in setting up what theology is all about. And then the third is that you can get some constructive theology inferences for theology, but they're speculative. They're problematic. And you can say that there are strong theological conclusions. The fifth is that the Asian Buddhism, and Zen, all the rest, quantum mechanics conclusions converge, and that they are really only two faces of a single entity. And the names there are Bohm and Capra. And then finally, what I will be discussing in this talk, that Aristotelian, I've misspelled Aristotelian, well, we'll forget about that, and Thomistic philosophy do explain quantum mysteries. And there are many authors here. I'll give some specific references at the end of the talk. Now, I'm grateful to Dr. Mahfoud for giving some explanations about metaphysics, but I want to give my own explanation so you'll see where I'm coming from. And so if I'm talking metaphysics with a physics accent, I hope you'll forgive me. So we have these terms: substance, form, accidents. What are they? Let's look at a concrete example, which I always like to do. An ice cube melts when it's heated and becomes liquid water. The substance, the ice cube, water, frozen water, remains the same when the agent, that is, the agent is heat, changes it to liquid. Its properties, which are called accidents, change on this transformation: shape, hardness, solidity, etc. Now, let me add something. I asked two artificial intelligence agents, the one from Bing, I guess, and ChatGPT, is this a change of substance? And I got two different answers. So I don't think it's a change of substance, but you might say that it was. I'm not that confident of what the substance is to actually make that distinction. But in any case, you get liquid water. Now, there are some more terms that are used: actus, the state of being, and potentia, the possibility of existence. The water is in a state of being, actus, as an ice cube, and it has the potentia of being liquid if a suitable transformation agent, heat, is applied. The liquid water has the potentia of being gas or steam if more heat is applied. And we have an interesting molecular simulation of these dynamics. Here we have a picture of an ice cube, water molecules arranged in a hexagonal array. They're vibrating internally, getting more and more energy as heat. Now, suddenly, the structure is broken as sufficient heat is applied, and they become liquid. They're still close together, and there's still sort of holes in there, and they're still bound together by hydrogen bonds. And now even more heat is applied, and whoosh, all of a sudden they separate, and you get not just a condensed phase liquid water, you get steam. All the water molecules are separate. So that's an interesting picture of explaining this on a molecular level. Well, let's go now and say, what does this have to do with Aristotelian Thomistic metaphysics? And here's a quote from Heisenberg that I think was the starting point for a lot of this. But the atoms of the elementary particles themselves are not as real. They form a world of potentialities or possibilities, or one of true facts. And then the philosopher Wolfgang Smith, what does all this have to do with Heisenberg's contention to the effect that quantum systems constitute a kind of Aristotelian potentia? That's the term that was used, that he used. This is what must now be explained, and this is from Smith's book, Quantum Enigma. And here are some more references. Kastner, Stewart, Kaufman, and Michael Everson. It is argued that quantum theory is best understood as requiring an ontological duality. That means a duality of how things are or how they be, by two concepts: res extensa, that is res things, and res potentia. things that are potential, or the latter is understood per Heisenberg's original proposal. That's an article in 2017. And then Robert Coons has articles, Gil Saunders has articles, and Alfred Dreesen has articles, and I'll give the references more specifically later at the end. Let's talk a little bit at the beginning now about the Kastner-Kaufman-Epperson, denoted as KKE, what they have to say. There are two ways of looking at this, I think. One is to use just these concepts of potentia and actus and use those in quantum mechanics. And the other is to take the whole framework of Aristotelian metaphysics, Thomistic metaphysics, and try to put quantum mechanics in that context. KKE talk about a real thing that can be perceived directly by measurements. The res potentia are also real, but cannot be perceived by sense or instruments. And their proposition is that the act of measurement converts a res potentia to res extensa, as in the double slit experiment. And they explain entanglement, that measurement removes all but one of the entangled states. And again, we can use the husband-wife voting as an example. Well, let's go a little bit deeper. Here's Wolfgang Smith with his book, The Quantum Enigma. I'll say a little bit about Wolfgang Smith. He was a boy genius. He got his PhD at the age of 18 or 19, I think, and has published a lot on this. He's the same age as I am, but has accomplished quite a bit more looking at all these things. First of all, his proposition is that there are two realities, that there are two kinds of external objects. There are what are called corporeal objects, which can be perceived, and physical objects, which can be observed only indirectly through instrumental physics. So, and every corporeal object X is associated with a physical object Sx, from which it derives all its quantitative attributes. And what he says measurement is that that you have a transition of being, ontological being, change from the physical to the corporeal domain. There is no Schrodinger's cat because corporeal objects are not superposed. They're simply aggregates. They're not simply aggregates of particles, but they're something more. And so he criticizes contemporary physics, but at the same time, he says that it's discovered an intermediate level of existence, that is this physical, this realm of being in which physical objects occur, the physical universe. And he says that you can explain more fully the difference between the corporeal object X and its physical object. And that's the third point down here. I'll come to that. The first first proposition is that there's a distinction between potency and act for a substance. First, back to Aristotle, the distinction between potency and act for a substance. For example, a seed is a tree in potency and a tree is a tree in act. Second, form is an act, capacity for being. To be more specific, there is what is called substantial form. So a substance has two aspects about it. The matter, that is that from which it's formed, and its form, its whatness. And here's the critical point from Aquinas. The act of being is the most intimate element in anything, and the most profound element in all things, because it is like a form in regard to all that is in the thing. So this is what introduces the concept of substantial form. And according to Smith, the substantial form is what distinguishes a corporeal object X from its counterpart, physical object SX. It is this form that bestows upon X its corporeal nature and specific essence. What presents itself to the eye of a physicist as an aggregate, a physical object of quantum particles, is in fact a corporeal object because it has substantial form. As parts of X, these putative particles are no longer visible and can no longer, strictly speaking, be considered as particles. They participate in the being of that entity in its substantial form. Since physical particles lack essence, they lack being. That's a quote. I'm going to come back to that later on. And you recall this, our water molecule, our piece of ice, and see what you think in terms of that representation of the water molecule and how it fits in with that statement. Because quantum objects in a corporeal object no longer exist as separate physical objects, quantum superposition no longer applies. There are no Schrodinger cats. And we represent microscopic physical objects as systems defined by observables that will be measured by some instrument. Quantum restriction. It is not possible to measure all the possible observables of a system simultaneously, according to the Heisenberg uncertainty principle. Now, what is the act of measurement? And this is perhaps the most profound part of Smith's explanation. His idea is that that space-time is just part of reality, that the universe exists as the worm Ouroboros in the picture at the right. And that when we speak of time, it has to do with, say, perhaps certain places on this worm. But according to God, there is no time. We all know that God is eternal. And this picture of a measurement, the idea of a measurement is that it is done by God. In other words, the arrow here, that gray arrow from the thing in the center, God is at the center of this circle, is what does the measurement. So that every time you have a measurement of a quantum system, you have what he calls a cosmogenetic act, which participates in the single act of creation. Whether the physicist realizes it or not, in the phenomenon of state vector collapse, he is picking up the cosmogenetic act, not hypothetically in some stipulated explosion that is supposed to have occurred so many billion years ago, but actually in the here and now. And that's from, all right, so let's go to some final thoughts, questions. And I'm not trying to make any conclusions myself on this. First of all, ask yourself, does the introduction of Aristotelian Thomistic metaphysical concepts explain any quantum mysteries? And as a part of this, you want to ask, if you take these concepts of potentia and actus by themselves to explain quantum mysteries, is that sufficient? Or should you do that in the full framework of Aristotelian Thomistic metaphysics, an ontology given by that? And what about Wolfgang Smith's radical new ontology? Are there some propositions that are difficult to accept? My answer to that question is yes. And what I'm thinking about here, my experience, scientific experience, has been in the NMR and MRI. And I'm thinking of this MRI image of the head And what you're seeing is a representation of water protons acting in a magnetic field, undergoing transitions by radio frequencies. And these are all quantum objects, and they're behaving as quantum objects. They're influenced by their environment. The water in brain tissue is different than the water in spinal fluid, and so the protons will see different fields. And you see that again in this MRI image, but they're all acting as quantum objects. And so I'm trying to reconcile that, and maybe I'm just being dense, but it's hard for me to do so with Smith's picture. Well, finally, let me give you some references. These are all listed here. I have given links which you can copy. I particularly recommend Robert Kuhn's as a very profound and fundamental and rigorous discussion. And in this, he gives, in his article about thermal substances, and I couldn't talk about that. It would have taken forever, and I don't really understand it well enough to give a good talk about it. An ontology of how the scientific worldview is best explained in context of Aristotelian metaphysics. And the two papers by Greg Jager and Gil Sanders are very clear, very good ways for those who aren't familiar with the philosophy or the quantum mechanics to understand their relation. I recommend both of those very highly. And with that, I will conclude and await questions, which I hope to be able to answer, but I may not. And thank you all.